Welcome to The Sleepy Physicist. If this helps you rest, consider leaving a like or subscribing. It helps others find this space too. There are objects in physics that exist perfectly on paper. The equations balance, the symmetries hold. Every term fits where it should, and the mathematics produces something clean and complete. But the universe is not made of paper. It is made of time and motion and consequence, and not everything that can be written can survive being real. White holes are one of these things. They appear in the same equations that describe black holes. The math is rigorous. If you reverse the direction of time in the equations governing a black hole, you get a white hole. It is not speculation. It is not a guess. It is a direct consequence of general relativity, the theory that describes how mass and energy curve space-time. And yet no one has ever seen one. No telescope has detected one. No gravitational wave signal has hinted at one. They exist in the structure of the theory, but not in the structure of the cosmos. This is not unusual. Physics is full of solutions that are mathematically valid but physically absent. There are solutions to Maxwell's equations that describe electromagnetic waves travelling backward in time. There are solutions to the Schrödinger equation that place particles in impossible superpositions. The equations do not care. They generate every possibility. It is the universe that selects. White holes fail this selection. The reason is not dramatic. It is not that they explode or collapse or tear space-time apart. It is quieter than that. They fail because they cannot persist. They cannot connect to the rest of the universe in a way that allows them to continue. A white hole would need to exist in a state of total rejection. Nothing could fall into it. No particle, no photon, no gravitational wave. Everything that approached would be turned away, not by force, but by the structure of space-time itself. The boundary of a white hole, its event horizon, would be a surface from which nothing could enter, only leave. But space-time is not passive. It responds to everything in it. A white hole sitting in the universe would curve space-time around it. That curvature would affect nearby matter and light. That matter and light would in turn affect the white hole. And here is where the problem begins. The interaction between a white hole and its surroundings would destabilize it. Not instantly, but inevitably. The white hole would begin to change, to warp, to lose the exact conditions that allowed it to be a white hole in the first place. Think of it as a shape that cannot hold. A white hole is a solution to Einstein's equations, but it is a fragile solution. It requires perfect conditions, conditions that the universe, with its clutter of stars and gas and radiation, cannot provide. The moment a white hole interacts with anything, even the faint background radiation left over from the Big Bang, it begins to break. It does not shatter. It does not vanish in a flash. It simply stops being what it was. There is another problem, deeper and stranger. White holes would have no past. A black hole forms from something, a collapsing star, a concentration of mass. It has a history. You can trace it backward. But a white hole cannot form this way. It would have to simply appear, already expelling matter and light, with no cause, no origin, no prior state. The equations allow this. The universe does not. Causality is not a law written into the equations of physics, but it is a pattern the universe follows almost without exception. Events have causes. Effects follow from prior states. White holes would violate this pattern, not by breaking a rule, but by existing without a backstory. This makes them ghosts, not in the sense of being supernatural, but in the sense of being disconnected. They would have no thread linking them to the past, and without that thread, they have no way to anchor themselves in time. Duration requires connection. To last, an object must be tied to the flow of causality, must participate in the exchange of energy and information that binds the universe together. White holes would refuse this exchange. They would push everything away, and in doing so, they would push themselves out of existence. There is a kind of beauty in this. The equations of general relativity are time-symmetric. They do not distinguish between past and future. If you reverse time in the equations, you get valid solutions. White holes are one of those solutions. They are the time-reversed twins of black holes. But the universe is not time-symmetric. It has a direction. Entropy increases. Causes precede effects. Heat flows from hot to cold. This asymmetry is not written into the fundamental laws, but it emerges from them. And it is this asymmetry that erases white holes. A white hole would be an island of reverse time in a universe that flows forward. It would not belong. The universe would not destroy it actively. It would simply fail to support it. The conditions that allow a white hole to exist for even a single moment would dissolve as soon as they appeared. The white hole would not explode, it would not decay, it would just cease, like a ripple that never completes or a note that cannot sustain. What remains is the question. If the math is correct and the solution is valid, why does the universe reject it? The answer lies not in the equations, but in what happens when the equations meet reality. Reality is messy. It is full of disturbances, fluctuations, interactions. White holes require perfection. They require isolation. And the universe does not provide isolation. It connects everything eventually. The thought lingers. White holes are possible but not sustainable. They are answers to a question the universe does not ask. Gravity does not feel like a force when you experience it. You sit in a chair, you stand on the ground. The sensation is of being held, not pulled. But this is because you and the earth are always falling toward each other, and the ground interrupts that fall. Gravity is not a pulling force in the way we imagine forces. It is the curvature of space-time itself. Mass tells space-time how to curve, space-time tells mass how to move. This is the essence of general relativity, and it is how black holes work. A black hole curves space-time so severely that nothing can escape once it crosses a certain boundary. That boundary is the event horizon. It is not a physical surface. There is no wall there, no material barrier. It's simply the point of no return. Light itself, moving at the maximum speed the universe allows, cannot climb back out of that curvature. Everything falls inward. White holes would do the opposite. They would curve space-time in such a way that nothing could fall in. The event horizon of a white hole would be a boundary that only allows things to leave, never to enter. Imagine trying to walk toward a place that moves away from you at exactly the speed you approach. You could never reach it. This is what a white hole does to everything in the universe. It retreats from approach, not through motion, but through the geometry of space-time itself. This sounds simple. Reverse the curvature, reverse the behavior. But the reversal is not symmetric in practice. A black hole pulls, and pulling is easy. The universe is full of objects that pull on each other. Planets pull on moons, stars pull on planets, galaxies pull on stars. Pulling is the default behavior of mass in space-time. It costs nothing. It happens naturally, inevitably, as soon as mass exists. Pushing is different. A white hole does not push in the sense of exerting a force. It does not send out beams of energy or emit particles that shove things away. It pushes by preventing entry. The curvature of space-time around a white hole is such that trajectories bend away. Light that tries to fall in gets deflected. Matter that approaches finds its path curving outward. This is not an active process. It is geometric. But geometry is not free. Maintaining this geometry requires that the white hole remain perfectly isolated. Any particle that managed to cross the event horizon would change the internal structure. Any photon that entered would add energy, add curvature, add complexity. The white hole would stop being a white hole. It would become something else, perhaps a black hole, perhaps something undefined. The mathematics does not describe what happens during this transition. The equations break down, but the result is clear. The white hole cannot survive the intrusion. An intrusion is inevitable. Space is not empty. Even the darkest regions between galaxies contain particles. Photons from the cosmic microwave background fill the universe. Neutrinos pass through everything. Gravitational waves ripple outward from distant events. A white hole sitting in space would be surrounded by all of this. The universe does not provide voids. It provides a thin but constant presence of matter and radiation, and that presence would press against the white hole's boundary. The boundary would hold for a moment. The event horizon is not fragile in the way a soap bubble is fragile. It is a feature of space-time itself, but space-time responds to what is in it. The particles and photons surrounding the white hole would create their own curvature, their own gravitational effects. Those effects would interact with the curvature of the white hole. The combined geometry would shift, the horizon would warp, and once it warps, it stops being a perfect barrier. This is not a violent process. There is no explosion, no sudden collapse. It is more like erosion. The white hole's ability to reject everything depends on the exact shape of its event horizon. If that shape changes even slightly, the rejection weakens. A photon that would have been turned away might now slip through. A particle that was deflected might now enter. Each intrusion changes the geometry further. The process accelerates. The white hole unravels. There is another issue, related but distinct. White holes would emit matter and light constantly. This is not optional. It is built into their structure. A white hole is by definition a region of space-time from which things emerge. But where does this matter come from? A black hole accumulates matter by pulling it in. The matter has a source. It comes from stars, gas clouds, anything nearby. A white hole has no such source. The matter it emits has no prior location. It simply appears at the event horizon and moves outward. This is not forbidden by the equations, but it raises a question the equations cannot answer. What determines how much matter is emitted? What determines its composition, its energy, its direction? A black hole's behavior is determined by what falls into it. A white hole's behavior has no such constraint. It would need to emit matter according to some rule, some initial condition. But there is no mechanism to set that condition, no process to establish it. The universe does not contain objects that emit without cause. Even radioactive decay, which seems spontaneous, follows probabilistic rules based on the internal structure of atoms. Even quantum fluctuations, which create particle pairs in empty space, follow conservation laws. White holes would emit without reference to anything. They would not conserve information in the way black holes do. They would simply produce, endlessly, until they stopped. And they would stop. The emission itself would destabilize the white hole. Each particle leaving the event horizon carries energy. That energy comes from somewhere, presumably from the white hole's own gravitational field. But as energy leaves, the curvature weakens. The horizon changes, the emission slows. Eventually the white hole would no longer have the energy to maintain its structure. It would fade, not into nothing, but into something ordinary. A region of curved space-time that no longer rejects entry, a region that might in fact begin to attract. This is the shape of rejection. It is not a wall. It is not a force. It is a geometry that cannot sustain itself in the presence of a universe that refuses to leave it alone. The white hole pushes everything away, but in doing so it exhausts the conditions that allow it to push. The harder it rejects, the faster it collapses into something else. What this means is that white holes, if they ever existed, would exist only briefly, not for millions of years, not for thousands, perhaps not even for seconds. The equations say they are possible. Reality says they are unsustainable. Between these two truths lies the territory where white holes flicker and fade, unable to persist. Space is not the empty stage we imagine it to be, the backdrop against which events unfold and objects move without resistance or interruption, but rather a participant in everything that happens, bending and flexing in response to mass, stretching thin in the vast regions between galaxies, bunching up near stars and planets, carrying information in the form of light and gravitational waves and fields that extend outward from every particle that exists. When you think of space this way, as something that responds and records, the idea of a boundary that nothing can cross becomes strange, not because it blocks, but because it erases the possibility of interaction. cuts off the exchange that binds the universe together into a coherent whole where cause follows effect and every object touches every other object, however faintly through the geometry they share. A white hole's event horizon would be this kind of boundary, one that moves away from anything trying to reach it, not through physical displacement, but through the way space-time itself is structured in that region, curved so sharply and in such a particular direction that all paths lead outward, all trajectories bend away, and the act of approaching becomes impossible not because you lack speed or strength, but because the closer you get, the more the space between you and the horizon stretches, the more your velocity redirects, the more your forward motion translates into sideways drift or backward recoil, until you are no longer moving toward the horizon at all, but simply circling it or retreating from it despite your intention, despite your effort. This is not a rejection you can feel in the ordinary sense because there is no force pushing against you, no wind blowing you back, no field exerting pressure on your body, only the shape of the path you are allowed to take through space-time, and that shape leads everywhere except inward. Light behaves the same way, photons streaming toward the white hole only to find their trajectories bending outward before they ever reach the horizon, their paths curving smoothly in arcs that carry them away, as if the white hole were surrounded by an invisible lens that redirects everything regardless of speed or energy or intent. And this happens not because the white hole actively does anything, but because the geometry around it simply does not permit inward motion the way the geometry around a black hole does not permit outward motion once you cross its threshold. But here is the difficulty. The thing that makes white holes unstable in a way black holes are not. A black hole sits in space and allows things to fall into it, accumulates mass and energy over time, grows denser and more gravitationally dominant as matter crosses the event horizon and adds to the singularity within. And this process costs nothing, requires no maintenance, follows the natural tendency of space-time to pull objects together under the influence of gravity. A white hole does the opposite, refuses everything, prevents accumulation, and this refusal means it cannot grow, cannot adapt, cannot respond to the universe around it in any way that would allow it to persist, and so it remains static in a universe that is never static, remains isolated in a cosmos that connects everything through gravity and light and the subtle curvature of space-time that extends infinitely outward from every object, no matter how small. The traces this leaves are not physical in the way a crater or a scar is physical, not marks etched into rock or metal, but disturbances in the fabric of space-time itself, ripples in the curvature that propagate outward like waves on a pond when a stone is dropped, except these waves carry information about the white hole's presence, encode its mass and spin and the particular geometry of its event horizon in the way they bend light passing nearby, in the way they nudge distant stars slightly off their expected trajectories in the gravitational lensing that would magnify and distort background galaxies into arcs and rings if anyone were positioned correctly to observe them. These traces would be the only evidence a white hole ever existed because the white hole itself leaves nothing behind when it ceases to be a white hole. No remnant, no debris, no lingering signature except the slight alteration of space-time that takes time to smooth out, to dissipate, to merge back into the general curvature of the universe. You might think of it as a stone skipping across water, touching the surface briefly and then gone, and the ripples it creates are all that remain, spreading outward in concentric circles that fade as they travel until the water is still again and nothing marks the place where the stone touched. White holes would be like this, brief interruptions in the structure of space-time that leave behind only the faintest indication they were ever there, and even that indication fades as the universe continues its expansion, as the curvature flattens, as the memory of the disturbance is diluted across increasingly vast regions of space, until it becomes undetectable, indistinguishable from the random fluctuations that fill the cosmos at every scale. The question becomes whether these traces are enough, whether a disturbance in space-time that lasts only moments and fades quickly can be considered evidence of existence or whether existence requires something more, something like duration or continuity or the ability to affect other objects over time. And if white holes lack all of these things, then perhaps they exist only in the way a thought exists, real in the moment it occurs but leaving no mark once it passes, no proof it ever happened, except the faint alteration in the structure of the mind that entertained it. What this suggests is that white holes might not be impossible but rather undetectable, not because they hide but because they last too briefly to be observed, appear and vanish in intervals shorter than the time it takes light to cross the distance from their event horizon to any observer who might be watching. And by the time the gravitational waves from their formation reach a detector, the white hole has already stopped being a white hole and transformed into something else, something ordinary, something that blends into the background of the universe without distinction. And so the boundary retreats, the traces fade, and nothing arrives because nothing can. The equations are beautiful. You've seen them before, maybe, in textbooks or documentaries, the Einstein field equations written out in their compact form with Greek indices and tensors looking more like poetry than physics. They relate the curvature of space-time to the distribution of mass and energy within it. 10 coupled nonlinear partial differential equations. Elegant, unyielding. They govern everything from the orbit of Mercury to the expansion of the cosmos itself, and they allow white holes, not as speculation, not as fantasy, as direct mathematical consequence. When you solve Einstein's equations for a spherically symmetric non-rotating mass, you get the Schwarzschild solution. It describes both a black hole and a white hole, two regions of space-time connected by the geometry. The black hole pulls everything inward past its event horizon. The white hole expels everything outward from its own. Same equations, same framework. Mirror images in the mathematics, but mathematics doesn't care whether something can happen. It only cares whether something is consistent with the rules you've written down. You can write an equation that describes a sphere with negative volume. The math works, the algebra is fine, but you cannot build one. You cannot find one. It exists as a solution, but not as an object. White holes are like this. The Schwarzschild solution contains them fully formed, embedded in the structure of space-time, described with the same precision as black holes, and yet they do not appear. No observation has ever hinted at one. No theoretical mechanism produces them. They sit in the equations like furniture in an empty room, perfectly placed but untouched, waiting for conditions that never arrive. Compare this to black holes. Black holes also seemed impossible once. The idea that a star could collapse so completely that nothing, not even light, could escape seemed absurd. Too extreme, too strange, but the universe provided a mechanism. Massive stars burn through their fuel. The outward pressure from fusion stops. Gravity takes over, the core collapses. If the mass is sufficient, nothing can halt the collapse. A black hole forms. The process is natural, inevitable even, given enough mass and time. White holes have no such process. There is no known mechanism that produces them. No collapsing star creates one. No quantum fluctuation generates one. No cosmological event seeds one. They would need to simply be there, already existing with no history, no origin, no causal chain leading backward to explain how they came to be. The equations allow them. Physics does not. Think of it like a lock and a key. The equations are the lock. A white hole is a key that fits perfectly. You can slide it in, it matches every tumbler. But the key has no hand holding it, no arm extending from it, no person behind it. It exists in isolation. A key that fits but has no user. A solution that works but has no source. You might wonder why this matters. After all, if the math is correct, shouldn't the universe follow it? Shouldn't every solution correspond to something real? But this assumes the universe is obligated to explore every possibility the equations allow. It is not. The equations describe what could be given certain conditions. They do not guarantee those conditions will ever occur. Think of it another way. The laws of thermodynamics allow you to unscramble an egg. There is no rule forbidding it. Every collision, every molecular interaction could, in principle, reverse. The yolk could separate from the white. The shell could reassemble. It is not impossible. It is merely so improbable that it will never happen in the entire lifetime of the universe. The math permits it. Entropy makes it vanishingly unlikely. White holes face a similar problem, but worse. It is not just that they are improbable, it is that the conditions required for their existence seem impossible to establish. A white hole would need to be born fully formed, ejecting matter and light from the start, with no prior collapse, no build-up, no process to explain the energy it contains. Where does that energy come from? What set it in motion? The equations do not answer. They simply describe the object once it exists. And once it exists, it cannot last. The universe is not a vacuum. Even in the emptiest regions of space there is radiation. The cosmic microwave background fills everything. Photons from distant stars cross every point. Particles appear and vanish in quantum fluctuations. A white hole sitting in this environment would be constantly disturbed. And disturbance for a white hole is fatal, because the white hole's event horizon is a boundary that must remain perfect. Any imperfection, any asymmetry, any slight deviation from the exact geometry described by the Schwarzschild solution, and the horizon begins to fail. It stops rejecting everything. It allows intrusion, and once something crosses inward, the white hole is no longer a white hole. It becomes undefined, or worse, it flips, turns into a black hole. The equations allow this too, so the math doesn't breathe. It sits on the page, unchanging, describing a structure that cannot survive contact with reality. A white hole is a solution in search of a universe that will never provide the conditions it needs. The equations are correct, the object is impossible. Not in the sense that it violates physics, in the sense that physics does not create it. You can write the equations for a universe where white holes are common, where they form naturally, where they persist and interact and shape the cosmos. The math would still work, but it would not be our universe. Our universe chose differently. It makes black holes, it does not make white holes, and the reason is not written in the equations. It is written in the way the universe began, in the direction time flows, in the tendency of entropy to increase, in the fact that causality points forward, always forward, never back. The math describes what is possible, the universe selects what is actual, and white holes remain on the page. Consider the structure of time as it relates to objects. A star begins as a cloud. The cloud collapses over millions of years. Atoms fuse, light escapes. The star shines for billions of years, then dies. The sequence matters. Each stage emerges from the one before. The star exists within a timeline that extends in both directions, backward to its formation, forward to its end. A white hole has no such timeline. It would need to begin emitting at some moment. Call it t equals 0. At t equals 0, matter and light pour outward from the event horizon. But what happened at t equals -1? What state preceded the emission? The equations provide no answer. They describe the white hole as already existing, already active, with no prior phase. The emission does not start because something triggered it. It starts because the white hole is there, and being there means emitting. This creates a boundary in time that feels wrong. Not wrong in the sense of violating a law, but wrong in the sense of being disconnected from causality. Every other object in the universe has a history. Particles are created in collisions or decays. Fields emerge from interactions. Even quantum fluctuations, which seem spontaneous, arise from the structure of the vacuum, from the uncertainty principle, from conditions that existed beforehand. A white hole would have none of this. It would simply be already in progress, with no explanation for how it arrived at that state. The emission itself carries another problem. If a white hole emits continuously, then over time it releases an infinite amount of energy. Or rather, it would if it lasted forever. But nothing lasts forever. Everything in the universe evolves, changes, responds to its surroundings. A white hole emitting energy must draw that energy from somewhere. The only source available is its own gravitational field, the curvature of space-time that defines it. As energy leaves, the curvature weakens, the white hole shrinks, eventually it exhausts itself. But how long does this take? The equations do not specify a time scale. A white hole could, in principle, emit for seconds or centuries depending on its initial mass and the rate of emission. Smaller white holes would fade faster, larger ones might persist longer, but none would last indefinitely. The act of emitting guarantees its own end. Now compress this timeline. Imagine a white hole that appears at one instant and vanishes almost immediately after. It exists for a fraction of a second. During that time it emits a burst of particles and radiation, then collapses or transforms into something else. From the perspective of an outside observer, the white hole flickers into existence and out again so quickly that it barely registers. The light it emits might not even reach distant observers before the object ceases to exist. This is not far from what the physics suggests. White holes, if they form at all, would likely be transient. They would emerge from specific initial conditions, perhaps at the birth of the universe during the Big Bang, when space-time was still chaotic and fluctuating wildly. In those early moments, the rules were less settled. Quantum effects dominated. Space-time itself was probabilistic, uncertain. White holes might have appeared in that environment, brief anomalies in the expanding cosmos, emitting their contents and then vanishing as the universe cooled and stabilized. If this happened, they are long gone now. The universe is nearly 14 billion years old. Any white hole formed in the first moments would have disappeared billions of years ago. Its emission completed, its structure dissolved. What remains would be the particles it released, scattered across space, indistinguishable from all the other matter and radiation filling the cosmos. There would be no way to trace them back to their source. No signature marking them as having come from a white hole rather than from some other process. This raises a quiet possibility. Some of the matter in the universe, maybe a small fraction, maybe none, could have originated from white holes. There is no way to prove it, no way to test it. The evidence has been erased by time, but the idea lingers, that in the first instant of the universe, when everything was compressed and strange, white holes existed for the briefest moment, ejected their contents and disappeared, leaving behind only the matter they released, now woven into galaxies and stars and planets and everything else. The strangeness is not in the emission itself, but in the asymmetry of it. A black hole accumulates. It pulls in matter over time, layer by layer, event by event. You can watch it grow. You can measure the mass crossing the event horizon. You can track the history of what fell in, at least in principle. A white hole does the opposite. It releases everything at once, or nearly so, with no history to track, no accumulation to measure. It is all output, no input, all consequence, no cause. And this asymmetry makes it incompatible with the universe as it exists now. The current universe has a direction. Time moves forward. Entropy increases. Events build on prior events. Information flows from past to future. A white hole reverses this flow, at least locally, at least at its boundary. It expels without having gathered. It outputs without having stored. It acts as if time runs backward in that one small region of space-time, and the rest of the universe cannot accommodate this. So the moment collapses, the white hole appears, if it appears at all, and then immediately encounters the reality around it. The cosmic microwave background radiation, the quantum fluctuations of the vacuum, the gravitational pull of distant matter, all of these press against the white hole's boundary, disturb its geometry, introduce imperfections. The event horizon warps, the emission slows, the structure fails, infinity pressed against an instant. That is what a white hole would be, an object that, if left alone, could emit forever, but which is never left alone, not even for a moment, and so collapses almost as soon as it begins. The mathematics describes the infinite potential. Reality imposes the instant, and between them the white hole flickers, too brief to observe, too fragile to persist. What this means is that white holes exist only at the edge of time, in the boundary between what could be and what is, in the moment before the universe decides they cannot continue. There is a certain weight to falling that feels inevitable once it begins, a sensation of surrender to gravity's patient insistence, and watching something fall in reverse does not create the opposite sensation, but rather something uncanny. Motion that traces the same path but carries none of the same meaning, because falling has direction built into it, direction that comes not from the trajectory, but from the experience of release, of letting go, of moving toward rather than away from, and when reversed the motion remains, but the release vanishes, and what remains looks like expulsion, like rejection, like something being forced outward along the exact path it once travelled inward. Black holes collapse, matter falls. The collapse takes time, sometimes seconds for a stellar core, sometimes millions of years for a supermassive black hole fed by slow accumulation. During the collapse, information about the infalling matter, its composition, its arrangement, its history, crosses the event horizon and becomes part of the black hole's interior. That information does not vanish in the classical sense. It persists, encoded somehow in the structure of the black hole, though precisely how remains one of the deepest puzzles in physics. The black hole remembers, in some abstract way, what fell into it. A white hole reversed from this would not restore that information. Reversing the film does not reverse the meaning. If matter emerges from a white hole, it emerges without history. There is no record of where it came from, no encoding of prior states, no memory preserved in its structure. The particles that leave carry energy and momentum, but they carry nothing else. They have no past. They simply appear at the event horizon and move outward, following trajectories determined by the white hole's geometry, but not by any process that preceded them. This is not restoration. It is creation without context. The pressure of emergence would feel different from the pressure of collapse if such a thing could be felt. Collapse is accumulation, a gathering inward, a compression that builds gradually as more mass adds to the whole. There is a logic to it, a sequence. Each layer of infalling matter presses on the layers beneath. The weight increases, the density rises, the event horizon grows outward to accommodate the added mass. It is a process that unfolds in stages, each stage comprehensible as the consequence of the one before. Emergence from a white hole would have no such stages. Matter would simply be there at the boundary, moving outward with no prior position, no journey through the interior, no gradual approach. One moment the event horizon is empty of crossing particles. The next, particles stream outward. The transition is discontinuous. There is no smooth evolution from one state to the next. The white hole does not build up to emission. It is always already emitting, or it is not emitting at all. There is no middle ground. And this discontinuity creates a problem for causality that is deeper than it first appears. In the universe as we experience it, every event has precursors. A photon is emitted because an electron dropped to a lower energy state. An electron dropped because it was in an excited state. It was excited because energy was absorbed. That energy came from somewhere else. The chain extends backward indefinitely, each link connected to the ones before and after. White holes break this chain. The particles they emit have no precursor. They are not the result of any prior event. They exist because the white hole exists, and the white hole exists without having been caused. Reversal implies symmetry, but the symmetry is superficial. Run a black hole backward and you get motion that looks like a white hole. Particles emerge instead of falling. Light escapes instead of being trapped. But the underlying structure is not symmetric because the universe itself is not symmetric in time. Entropy increases in one direction. Heat flows from hot to cold. Causes precede effects. These are not laws in the same sense that conservation of energy is a law, but they are patterns so consistent that violations seem impossible. White holes would violate all of them. The warmth of emitted particles would carry no trace of the white hole's interior because the interior cannot be accessed, cannot be examined, cannot be known even in principle. A black hole's interior is hidden behind the event horizon, but at least there is an interior, a region of space-time where the infalling matter exists even if no outside observer can see it. A white hole's interior is not hidden, but absent. There is no region where the emitted matter existed before emission. It appears at the boundary, fully formed, with energy and momentum but no prior location. This makes the white hole less a reversed black hole and more an inside-out singularity, a point from which things emerge rather than toward which they collapse. But the singularity itself has no content, no structure, no information to release. It is a geometric feature, a place where the curvature of space-time becomes infinite. But infinity here does not mean abundance. It means breakdown. The equations stop working. The predictions become meaningless. What happens at the singularity cannot be calculated, cannot be described, cannot be known. Black holes hide their singularities behind event horizons. White holes expose theirs, in a sense, by making the horizon a boundary from which everything originates. But this exposure reveals nothing because there is nothing to reveal. The singularity is not a place where information is stored. It's a place where information ceases to have meaning. Motion outward from this point carries momentum, but no message. The particles stream away. They interact with the rest of the universe. They collide, decay, transform. Eventually they become indistinguishable from any other particles. There is no way to identify them as having come from a white hole, no marker, no signature. They are ordinary matter, released under extraordinary circumstances, but the circumstances leave no trace on the matter itself. So the reversal is incomplete. Black holes gather, white holes scatter. The motions are opposite, the consequences are not. A black hole grows denser as it accumulates. A white hole grows weaker as it emits. A black hole influences its surroundings by pulling them inward. A white hole influences its surroundings by pushing them outward. But in both cases, information is lost. In the black hole, it disappears behind the horizon. In the white hole, it never existed in the first place. And so the film runs backward, but what it shows is not the undoing of the collapse. It is only the image of it, emptied of content, stripped of meaning. The white hole expels, nothing is returned. Start small. A single atom near the event horizon of a white hole. It approaches, carried by its momentum by the ambient motion of the gas cloud it belongs to, by the general drift of matter through space. It moves toward the boundary. The boundary moves away, not physically. The event horizon doesn't shift position like a wall sliding backward. But the geometry of spacetime near the horizon is such that all paths curve outward. The atom's trajectory bends. It never reaches the surface it was aimed at. Instead, it arcs away, deflected by the curvature, sent back into the surrounding space without ever making contact. This happens to every atom, every photon, every particle. Now expand the scale. A cloud of gas, millions of atoms drifting toward the white hole. Each atom individually deflected. Each photon redirected. The cloud as a whole cannot penetrate the boundary. But the cloud doesn't vanish. It remains nearby, surrounding the white hole, accumulating just outside the event horizon because it has nowhere else to go. The white hole deflects it, but the deflection is not strong enough to send it far away. The particles orbit, drift, accumulate. This accumulation changes the environment. The gas cloud has mass. Mass curves space-time. The curvature from the cloud adds to the curvature from the white hole. The combined geometry is no longer the simple clean solution described by the Schwarzschild metric. It becomes more complex, asymmetric. The event horizon begins to warp under the influence of the surrounding matter. You see the problem now. The white hole depends on a specific geometry to function. The event horizon must maintain a precise shape, a precise curvature, in order to deflect everything that approaches. Any deviation from this shape weakens the deflection. Particles that would have been turned away now find paths that bring them closer. Photons that would have bent outward now graze the horizon at shallower angles. And once a particle crosses the horizon, everything changes. The white hole is no longer a white hole. The interior geometry, which was supposed to remain inaccessible, now contains matter. That matter has energy. Energy curves space-time. The curvature inside the horizon shifts. The singularity at the center, if it even exists in the classical sense, responds to the new conditions. The white hole begins to transform. Into what exactly is unclear. The equations of general relativity describe white holes and black holes, but they do not describe the transition between them. There is no smooth mathematical path from one to the other. The transformation would involve regions where the equations break down, where quantum effects become important, where the classical description of space-time fails. What emerges on the other side of this breakdown is unknown. Perhaps a black hole, perhaps something hybrid, perhaps nothing stable at all. But the key point is this: the transformation is inevitable. You cannot have a white hole in a universe filled with matter and radiation without that matter and radiation eventually disturbing the white hole's geometry. And once disturbed, the white hole cannot recover. There is no mechanism to restore the precise conditions it needs. No feedback loop to correct the deviations. The instability grows. The horizon warps further. More particles cross. The process accelerates. This is instability without motion because the white hole itself does not move. It sits in space, static in its reference frame, emitting particles but not travelling. Yet it falls apart. Not because something strikes it, not because it runs out of energy in the usual sense, but because the universe around it presses inward, gently and constantly. adding small perturbations that accumulate over time until the structure can no longer hold. Think of it as erosion but faster. A cliff face erodes over centuries as wind and rain wear away the rock. Each gust of wind removes a few grains. Each raindrop loosens a small fragment. Individually, these effects are negligible. Collectively, they reshape the cliff. The white hole erodes in the same way, except the timescale is not centuries but perhaps microseconds. Each photon that approaches disturbs the geometry slightly. Each particle that drifts nearby adds its own small curvature. The disturbances compound, the geometry shifts, the horizon fails, and this happens even in the emptiest regions of space because there are no truly empty regions. The cosmic microwave background fills the universe. Roughly 400 photons per cubic centimetre left over from the Big Bang, cooled now to a temperature just above absolute zero. These photons are everywhere. They pass through galaxies, through stars, through the voids between clusters. A white hole sitting in this bath of radiation would be constantly bombarded. Each photon that approaches exerts a tiny gravitational effect. Each one curves space-time by an imperceptible amount, but there are trillions upon trillions of them. Over time, their combined effect is not imperceptible. The white hole's event horizon, which must remain perfect to function, cannot remain perfect in the presence of this constant disturbance. It warps, it buckles, it loses the exact shape required to deflect everything. And once it loses that shape, it begins to allow intrusions. Photons slip through, particles follow. The interior, which was supposed to be a region of pure outward flow, now contains inward moving matter. The white hole collapses into contradiction. This is why white holes cannot persist. Not because they are forbidden by the laws of physics, but because they are incompatible with the environment those laws create. The universe is not a vacuum. It is filled with fields and particles and radiation. Every object in the universe interacts with this environment. Black holes interact by pulling it in. Stars interact by emitting light and heat. Planets interact by orbiting and reflecting. White holes would need to interact by rejecting everything, but rejection is not a stable state. It is a balance that requires precision, and precision cannot be maintained in a universe that disturbs everything constantly. So the white hole stands still. It emits, it deflects, and quietly, without drama, it begins to fail. The contradictions accumulate, the geometry shifts, the boundary weakens, and eventually there is no boundary at all. Just a region of curved space-time, no longer special, no longer rejecting, blending into the rest of the universe as if it had never been distinct. Light travels through space without friction, without resistance, moving at its fixed speed through the vacuum, carrying information from distant stars and galaxies, crossing billions of light years without losing its direction or its energy, except to the slow redshift of expansion. The path light takes is determined by the curvature of space-time it moves through. In flat space, light travels in straight lines. Near mass, the lines curve. The sun bends starlight passing close to it. Galaxies act as lenses, bending and magnifying the light from objects behind them. This is not light being pulled. It is light following the straightest possible path through curved geometry. An event horizon is where this geometry becomes extreme. Around a black hole, space-time curves so sharply that light travelling outward from inside the horizon finds every outward path curving back inward. There is no escape trajectory. Every direction leads toward the singularity at the centre. The horizon itself is the boundary where this becomes true, the spherical surface marking the point of no return. Outside it, light can still escape if aimed correctly. Inside it, Escape is impossible regardless of direction or effort. A white hole's horizon would do the reverse in principle. Light approaching from outside would find every inward path curving back outward. The horizon would be a surface that nothing, not even light, could cross from the outside. All trajectories would bend away. An observer trying to send a signal toward the white hole would see that signal deflected, redirected, sent back into the surrounding space. The white hole would be perfectly reflective, not because it reflects like a mirror reflects, but because space-time itself refuses to allow inward motion past the boundary. But this refusal is not passive. Space-time does not simply sit in a fixed configuration. It responds dynamically to everything in it. A photon approaching the white hole carries energy. Energy has mass equivalence. Mass curves spacetime. The photon's approach, even if deflected, slightly alters the geometry near the horizon. The alteration is tiny, almost negligible for a single photon, but it exists, and the white hole must adjust to it. The horizon must maintain the exact curvature needed to deflect the photon, which means the horizon must respond to the photon's presence, which means the geometry cannot remain static. Now consider not one photon, but a constant stream. The cosmic microwave background provides this stream. Photons arriving from all directions continuously without pause, each one deflected, each one adding its small influence to the local curvature. The white hole's horizon must adjust to every single approach, must maintain the geometry that turns each photon away, must do this billions of times per second for every square meter of its surface. This is not a one-time adjustment. It is a continuous process. The horizon is not a fixed surface but a dynamic boundary, constantly responding to the environment, constantly recalculating the curvature needed to deflect the next incoming particle, the next wave, the next disturbance. And this recalculation requires that information about the approaching particles propagate through space-time, that the geometry update itself in response, that the white holes somehow know what is coming and bend space-time accordingly. But information travels at the speed of light. No faster, a photon approaching the white hole carries information about its trajectory, its energy, its momentum. That information reaches the horizon at the same moment the photon does. There is no advance warning, no time for the horizon to prepare. The adjustment must happen instantaneously or the photon crosses. And instantaneous adjustments are not possible in a universe where causality is local, where effects propagate at light speed, where space-time responds to changes rather than anticipating them. The problem compounds when multiple particles approach from different directions simultaneously, which is always the case in any realistic environment where radiation fills space uniformly and matter drifts in clouds and streams, rather than arriving one particle at a time along predictable paths. The white hole's horizon must deflect everything at once, must maintain a geometry that works for all incoming trajectories, must balance the curvature needed to turn away a photon from the north against the curvature needed to turn away a particle from the south. And these requirements may conflict, may demand incompatible geometries, may create stress in the structure of space-time itself. Stress in space-time is not metaphorical. General relativity describes space-time as a geometric object that can bend, stretch, compress, ripple. Gravitational waves are ripples propagating through space-time, carrying energy away from their source. And that energy comes from the stress of accelerating masses, of objects moving through curved regions, of geometry trying to settle into equilibrium but being disturbed before it can. A white hole facing constant bombardment from all directions would generate stress in the geometry around its horizon. stress that cannot dissipate because the bombardment never stops, stress that accumulates as each new disturbance arrives before the previous one has fully resolved. And stress seeks release. In solid objects, stress leads to cracks, fractures, structural failure. In space-time, stress leads to changes in geometry, to shifts in curvature, to deviations from the ideal configuration. The white hole's horizon, under constant stress from the need to deflect everything approaching it, would begin to deviate from the perfect shape required. The deviations would be small at first, a slight flattening here, a small bulge there, but each deviation weakens the deflection. Particles that should have been turned away now approach closer. Their influence on the geometry increases, the stress grows. The horizon begins to resemble a membrane stretched too thin, pulled in too many directions, unable to maintain its integrity under the constant demands placed on it, and like a membrane it would eventually tear, not literally because space-time does not tear, in the way fabric tears, but functionally, in the sense that the boundary stops functioning as a boundary, stops preventing entry, allows the first particles to cross, and once crossing begins it cannot be stopped because each particle that enters changes the geometry further, makes crossing easier for the next particle, accelerates the breakdown. At this point the white hole ceases to be a white hole in any meaningful sense, because the defining feature of a white hole is the horizon that prevents entry. And without that feature functioning, the object becomes something else, something undefined by the classical equations, something that exists in the transition between one state and another. And transitions are not stable, they are processes, and processes move toward completion. The horizon facing outward could not hold, not because it lacked strength, but because it required adjustment without time, coordination without communication, perfection without error. And the universe does not provide these things, it provides disturbance, constant and unavoidable, and disturbance is what the white hole cannot survive. Every star has a history written in its spectrum. The light it emits carries information about the elements inside it, about the fusion processes occurring in its core, about the temperature and pressure and composition of layers you can never directly observe. Astronomers read this light and reconstruct the star's past. They can tell you roughly when it formed, what materials it condensed from, whether it has already burned through its hydrogen or still has billions of years remaining. Every galaxy has a history visible in its structure. Spiral arms indicate recent star formation. Elliptical shapes suggest ancient collisions and mergers. The distribution of old stars versus young ones maps out the timeline of the galaxy's evolution. Dark matter halos reveal gravitational interactions stretching back to the early universe. Even black holes have histories. They form from collapsing stars or from the merger of smaller black holes. Their mass tells you something about their origin. Their spin reveals information about what fell into them and from which direction. The gravitational waves they emit during mergers encode the details of their final moments before coalescence. Everything about a black hole connects backward to events that preceded it. A white hole would have none of this. It would not form from anything. There would be no prior state to examine, no process to trace backward, no sequence of events leading to its existence. The white hole would simply be present, already functioning, already emitting, with no causal chain extending into the past. This is not a minor detail. It is a fundamental break with how objects exist in time. Consider what this means for the matter it emits. A white hole releases particles and radiation continuously. Those particles have energy, momentum, mass. They interact with the universe around them. They can be detected, measured, analysed. But where did they come from? In every other scenario, emitted particles have an origin. A star emits photons because fusion reactions in its core produce them. A radioactive nucleus emits particles because quantum tunneling allows them to escape. Even Hawking radiation from black holes, which seems to emerge from nothing, actually arises from quantum fluctuations near the event horizon. White holes offer no such mechanism. The particles they emit do not come from fusion, from decay, from quantum effects, or from any process occurring inside or near the white hole. They simply appear at the event horizon, already in motion outward, already carrying the properties they will carry into the universe beyond. There is no interior process generating them, no fuel being consumed, no reaction taking place, just emergence without source. This violates a principle deeper than any written law. The universe operates on precedent. Effects follow causes. States emerge from prior states. You can trace the lineage of any particle back through time, through collisions and interactions and transformations, all the way to the Big Bang if you follow carefully enough. Every piece of matter in your body was once part of a star, before that part of a nebula, before that part of the early universe's plasma. The chain is unbroken. A particle from a white hole would have no chain. It would be a dead end. You could not trace it backward. There would be no prior position, no earlier momentum, no transformation that produced it. The particle would be genuinely new, appearing at the moment of emission, with no antecedent, no cause, no reason. And the universe resists this kind of novelty, not through any explicit prohibition, but through the interconnectedness of everything that exists. Events are woven together, information flows from past to future. Objects are embedded in context that explain them. White holes would be contextless. They would sit in space-time like foreign bodies, objects that do not belong to the timeline they inhabit, that have no roots in the past and therefore no stable connection to the present. This disconnection would make them vulnerable, not to attack, not to decay in the ordinary sense, but to dissolution. The universe stabilizes objects through their connections. A planet orbits a star orbits the galactic center, galaxy moves within its local cluster. These connections are gravitational, electromagnetic, informational. They bind objects into the larger structure of reality. A white hole would refuse these connections in a fundamental way. It would emit without having gathered. It would influence without being influenced. It would exist in the present without having existed in the past. And this kind of existence is unsustainable because the present is not a separate thing from the past. The present is continuous with it, flows from it, carries it forward. Objects that lack this continuity lack the anchoring that allows persistence. Think of it like a story with a missing chapter. You can read the current chapter. The words make sense, the sentences are grammatical, but when you try to understand why events are unfolding this way, why characters are in this location, why certain objects are present, you find nothing. No prior chapter explains it. The story simply begins mid-scene, with no setup, no introduction, no foundation. It works on the surface but fails under examination. White holes would fail under examination in the same way. Their presence would raise unanswerable questions, not philosophical questions, but practical ones. Where did the emitted matter originate? What determined its properties? Why this amount of energy and not another? The answers would not exist because the questions assume a causal history that is absent. The white hole would be an answer without a question, a conclusion without premises, an effect without a cause. And the universe, which operates through cause and effect even when those causes are subtle or difficult to trace, would find no way to accommodate this. the white hole would remain alien, separate, unintegrated. And separation in a universe where everything connects through gravity and fields and space-time curvature is not stable. The white hole would persist only as long as it maintained perfect isolation. But perfect isolation is impossible. The moment it interacts with anything, the moment a single photon from the cosmic microwave background grazes its event horizon, it begins to acquire a history, a small one, a partial one, but enough to start the process of integration. And integration destroys what made it a white hole. Because a white hole is defined by its lack of history, by its refusal of causality, by its existence outside the normal flow of time. Once it begins to participate in that flow, once it gains even the slightest causal connection to the rest of the universe, it stops being a white hole and becomes something ordinary, something that can be traced backward, something that fits. The past is not optional. Not in a universe where time flows forward and events build on what came before. White holes would need the past to be optional, and so they would remain impossible. Not by law, but by context, not by prohibition, but by incompatibility. Sound requires a medium. Air, water, metal, something that can vibrate and carry the disturbance from one place to another. In the vacuum of space, sound cannot propagate. There are particles, yes, but too few and too dispersed to sustain the kind of wave motion sound depends on. So when we talk about sound near a black hole or white hole, we speak metaphorically. We mean signals, information, any disturbance that could travel from one location to another. Near a black hole, signals move inward but never outward. A photon emitted just inside the event horizon travels toward the singularity. It has no choice. The curvature of space-time inside the horizon is so extreme that all forward motion in time corresponds to inward motion in space. The photon moves through time, therefore it moves toward the center. If you could somehow survive inside a black hole's event horizon and shine a flashlight outward, the beam would curve back, wrapping around the curved space-time, eventually intersecting your position from behind. This creates a kind of acoustic isolation, though not acoustic in the literal sense. Nothing inside can send information outward. The interior is cut off from the exterior completely. Events occurring inside leave no trace outside. The black hole's exterior surface, the event horizon, acts as a one-way membrane. Information crosses inward, but never returns. The center is silent to the universe beyond, not because it produces no signals, but because those signals cannot escape. A white hole would invert this. Signals would move outward, but never inward. A photon approaching from outside would find its trajectory bent away before reaching the event horizon. You could aim a laser at a white hole, and the beam would curve around it, redirected by the space-time curvature never touching the surface. The white hole would be unreachable by any external signal. You could not send it information. You could not disturb it with radiation or particles or gravitational waves. It would exist in perfect isolation from anything outside, but this isolation creates a profound asymmetry. Black holes can receive. They accumulate information, even if that information is lost to outside observers once it crosses the horizon. The black hole grows as it consumes. It changes in response to what falls in. It is connected to the universe through this one-way flow. White holes cannot receive. They can only emit. There is no input, no way for the external universe to influence them, no channel through which information can flow inward. This makes them deaf to their surroundings. Consider the implications. A white hole sitting in a galaxy cannot sense the presence of nearby stars. It cannot detect the gravitational pull of passing planets. It cannot respond to the radiation from a supernova exploding light years away. All of these events produce signals, photons, gravitational waves, particle streams, but none of those signals can reach the white hole. They bend away. they deflect. The white hole remains untouched, unaware, isolated, and isolation is expensive, not in the sense of requiring energy, but in the sense of requiring precision. The white hole must maintain a geometry that deflects every possible approach, every particle trajectory, every photon path, every gravitational ripple. The curvature must be exactly right to turn everything away, and maintaining this exactness means the white hole cannot adapt. It cannot adjust to changes in its environment. It is locked into a fixed configuration, unable to evolve, unable to respond. Compare this to ordinary objects. A planet feels the gravitational tug of a passing comet and shifts slightly in its orbit. A star absorbs a cloud of gas and grows hotter, brighter. Even black holes respond to their surroundings. They accrete matter. They emit Hawking radiation, slowly evaporating over timescales longer than the current age of the universe, but still interacting, still connected. These objects exist in relationship with the universe around them. They receive input and produce output. The flow is bidirectional, or at least not completely one way. White holes allow no such flow. They emit, but they do not receive. They influence, but they are not influenced. This one-way relationship is unstable because the universe does not support true independence. Everything is gravitationally bound to everything else, however weakly. Light from distant galaxies reaches every point in space. Neutrinos pass through planets and stars without stopping. The cosmic web of matter and energy connects all regions, all objects, all events. A white hole would stand outside this web. It would be a node with no incoming connections, only outgoing ones. Information would flow away from it, but never toward it. And this breaks the symmetry that underlies physical law. Conservation of energy, conservation of momentum, conservation of information, all of these rely on balanced exchanges. Energy leaves one system and enters another. Momentum transfers from one object to another. Information propagates from source to destination. White holes would violate this balance by participating only on the output side. The pressure to correct this imbalance would come from spacetime itself. Spacetime is not passive. It curves in response to mass and energy. It carries waves when objects accelerate. It evolves according to equations that link its shape to its contents. A white hole sitting in spacetime without accepting any input creates a geometric tension. The curvature around it tries to connect it to the rest of the universe, tries to establish the normal flow of information, tries to integrate it into the larger structure. But the white hole's geometry resists. It deflects. It refuses. This refusal cannot last indefinitely. The cosmic microwave background presses against the event horizon constantly. Each photon deflected adds a tiny stress to the geometry. Gravitational waves from distant mergers pass through the region, causing minute flexing in the spacetime around the white hole. Dark matter, if it exists in the vicinity, exerts its gravitational influence, pulling gently on the surrounding curvature. All of these effects are small. None of them individually would disrupt the white hole, but they accumulate, they compound, they never stop. And the white hole has no mechanism to dissipate the accumulated stress, because dissipation requires interaction, requires give and take, requires absorbing some of the incoming influence and adjusting in response. The white hole cannot absorb, cannot adjust. It can only maintain or collapse, and maintenance requires perfection that the universe's constant perturbations make impossible. The silence at the center is not peaceful. It is brittle. It is the silence of something cut off, something isolated, something that cannot hear the universe calling it back into relationship. And that silence, that isolation, becomes the source of the white hole's failure. Not because isolation is forbidden, but because maintaining it costs more than the white hole has to spend. Eventually, the geometry buckles. A photon crosses inward, then another. The silence breaks, not with sound, but with the restoration of connection, the reintegration of the white hole into the universe's web of interaction. And once reconnected, it ceases to be white, ceases to be separate, ceases to exist as the isolated object it needed to be. The center grows quiet in a different way, not the silence of refusal, but the silence of dissolution. Imagine the entire observable universe for a moment. Galaxies scattered across billions of light years, clusters and superclusters forming webs of matter, vast voids between them, dark and nearly empty. Now zoom in, pick a single galaxy, then a single star system within it, then the space around a single planet, then a region just above that planet's atmosphere, then a cubic meter of that region. Even here in this small volume there is matter. You cannot find true emptiness. Photons pass through constantly. Cosmic rays, high-energy particles from distant sources, cross the space every second. Neutrinos stream through unimpeded. The interplanetary medium contains atoms, mostly hydrogen, a few per cubic centimetre. Not much, but not nothing. Space is thin, but it is occupied. A white hole would sit in this occupied space. Now zoom in further. Focus on the region immediately surrounding the white hole's event horizon. The boundary itself is not physical. It has no thickness, no substance. It is simply the mathematical surface where space-time curvature becomes such that inward motion is impossible. Just outside this surface, space-time is still curved but not prohibitively. Matter can exist there. Particles can drift there. And they do. The hydrogen atoms in the local environment don't vanish when a white hole appears. They remain in motion, drifting according to their velocities, responding to gravitational influences from nearby objects. Some of these atoms, through random motion or systematic drift, approach the white hole. Their paths curve as they near the horizon. The curvature deflects them. They don't reach the boundary. They loop around it, following geodesics that bring them close and then carry them away, but not all the way away. An atom deflected by the white hole's curvature doesn't necessarily gain enough momentum to escape the region entirely. It might be deflected into an orbit, not a stable orbit like a planet around a star, but a chaotic, precessing path that keeps it near the white hole without crossing the horizon. Over time, more atoms arrive. More get deflected into similar paths. They don't collide often, space is too empty for that, but they accumulate. The density of matter in the region just outside the event horizon begins to increase. This accumulated matter has mass. Mass curves space-time. The curvature from the accumulated atoms adds to the curvature from the white hole itself. The combined geometry becomes more complex. You no longer have the clean, symmetric solution that describes an isolated white hole in empty space. You have a white hole surrounded by a diffuse shell of matter, and that shell changes everything. The white hole's event horizon depends on a specific curvature profile to function. The geometry must be exactly right to deflect all incoming particles. But the presence of the matter shell alters the geometry. The curvature near the horizon becomes asymmetric. One side, where matter has accumulated more densely, curves differently than the opposite side. The horizon itself begins to distort. It bulges slightly in some places. It flattens in others. These distortions weaken the deflection. A particle approaching the bulged region finds the curvature less sharp than it should be. Its trajectory bends, but not quite enough to carry it completely away. It grazes closer to the horizon than particles approaching from other directions, And if the distortion grows, if more matter accumulates and the bulge becomes more pronounced, eventually a particle will graze close enough that it crosses. Once crossing begins, it accelerates. The first particle to cross the horizon adds its mass to the white hole's interior. This changes the internal geometry. The white hole, which was in a delicate equilibrium, tips toward instability. The horizon distorts further. More particles find their way across. Each crossing makes the next easier. The process feeds itself. The matter shell, which started as a minor perturbation, becomes the mechanism of the white hole's dissolution. You might wonder why the white hole doesn't simply push the matter away more forcefully. But the white hole doesn't push in the active sense. It doesn't exert a force. It simply has a geometry that deflects. The deflection depends on the curvature being maintained. If the curvature changes due to external influences, the deflection weakens. There's no feedback mechanism to strengthen it, no way for the white hole to adjust its geometry to compensate for the accumulating matter. The white hole is static. The environment is dynamic. The dynamic always wins. Consider the timescale. How long would this take? In a dense environment, say near the center of a galaxy where gas clouds are thick and star formation is active, the accumulation would happen quickly. Matter would pile up around the white hole within days or weeks. The distortion would grow rapidly. The horizon would fail within months. In a sparse environment, intergalactic space far from any significant sources of matter, the process would take longer. But even in the emptiest regions, the cosmic microwave background provides a constant flux of photons. Each photon deflected adds a tiny amount to the cumulative stress. Over time, even this diffuse radiation would be enough. The white hole cannot escape its neighbors. It cannot move away from the matter surrounding it. It has no propulsion, no mechanism for displacement. It sits in space, subject to whatever local conditions exist. And those conditions are never perfectly empty, never perfectly symmetric, never perfectly still. There is always something nearby, always some perturbation, always some source of accumulation. And accumulation is fatal. Black holes handle accumulation by growing. The matter that falls in makes them larger, more massive, more gravitationally dominant. They adapt to their environment by consuming it. White holes cannot adapt, they cannot grow, they can only emit. An emission doesn't strengthen them, it weakens them. Each particle leaving carries energy away. The white hole diminishes while the matter around it accumulates. The imbalance grows. Eventually, the white hole is overwhelmed not by a dramatic collapse, but by the gradual encroachment of its surroundings. The matter shell presses inward, not through force but through the simple fact of its presence, its mass, its curvature. The white hole's geometry buckles under the influence. The horizon fails, and what was once a white hole becomes a region of space-time indistinguishable from any other, just slightly more curved, just slightly denser, blending into the background as if it had never been separate at all. The question of neighbours is the question of isolation, and the answer is that isolation is impossible. Everything has neighbours. Everything is embedded in an environment. White holes would need to exist apart, untouched, uninfluenced. But the universe provides no such places. It fills every region with something, however thin, and that something is enough to erase them. Consider the lifespan of structures across cosmic time, beginning with the longest and moving toward the briefest, as a way of understanding where white holes would sit if they could sit anywhere at all in the hierarchy of duration. Galaxies persist for tens of billions of years, their structures maintained by dark matter halos and the gravitational binding of billions of stars, and even as individual stars are born and die within them. The galaxies themselves remain recognizable across epochs, their spiral arms reshaping slowly, their central black holes growing gradually, their overall form enduring through most of the universe's history, until eventually, in the far future, they will merge with neighbors or drift alone into the expanding void where star formation has ceased, and all that remains are cooling remnants. Stars themselves last millions to trillions of years depending on their mass. The smallest red dwarfs burning hydrogen so slowly they will outlive the current age of the universe many times over, while the most massive stars exhaust their fuel in mere millions of years before collapsing into neutron stars or black holes. But even the brief lives of massive stars are luxuriously long compared to most phenomena in physics, long enough for planets to form around them, for chemistry to evolve on those planets, for complexity to emerge if conditions allow. Planets orbit for billions of years, their surfaces changing through geological processes, atmospheres evolving, climates shifting, but the planets themselves remain intact across timescales that dwarf human history. Their existence stable enough that we can predict their position centuries into the future with extraordinary precision, their gravitational interactions with their parent stars and sibling planets following patterns established at their formation and likely to continue until their stars die or external forces disrupt the system. Atomic nuclei, once formed, can persist almost indefinitely if they are stable isotopes, their protons and neutrons bound together by the strong nuclear force in configurations that require no maintenance and face no decay, while unstable isotopes decay over timescales ranging from billions of years for uranium-238 down to fractions of a second for highly unstable artificial elements. But even the shortest-lived nuclei exist long enough to be detected, measured, studied, their decay products analyzed to confirm their brief presence. Particles created in high-energy collisions, muons, pions, tau leptons, last microseconds or nanoseconds before decaying into lighter particles, their existence so brief that they travel only millimeters or centimeters from their creation point before transforming, and yet these lifetimes are long enough to observe, long enough to measure with precision instruments, long enough to build entire branches of physics around understanding their behavior and decay modes. Quantum fluctuations, the virtual particles that appear and disappear in the vacuum, exist for timescales determined by Heisenberg's uncertainty principle, typically on the order of 10 to the power of minus 21 seconds or less, borrowing energy from the vacuum and paying it back so quickly that they leave no lasting trace except in their subtle effects on measurable quantities like the Lamb shift in hydrogen atoms or the Casimir effect between conducting plates. And even these fleeting disturbances in the quantum fields are well-defined phenomena with predictable consequences. White holes, if they could exist at all, would sit somewhere near the bottom of this hierarchy, or perhaps below it entirely, their duration measured not in microseconds but in timescales so short that the concept of duration becomes questionable, because the conditions that would permit a white hole to form are the same conditions that would immediately destabilize it, and the transition from formation to dissolution would occur faster than information could propagate across the white hole's own event horizon. The event horizon of a white hole has a radius determined by its mass, and for a stellar mass white hole, this radius would be a few kilometers, which means light would take roughly 10 to the power of minus 5 seconds to cross from one side of the horizon to the other, and this crossing time represents the minimum duration over which the white hole could be said to exist as a coherent object, because space-time curvature and information propagation happen at light speed, and nothing can coordinate faster than that. But the instabilities that destroy white holes operate faster than this coordination time, not in the sense of superluminal effects, but in the sense that the white hole's geometry cannot stabilize before the first perturbations arrive, cannot establish itself as a coherent structure before the cosmic microwave background, photons already present in the space it occupies begin deflecting off the forming horizon, and these deflections immediately begin the process of geometric distortion that leads to horizon failure. The white hole does not get a moment to settle, does not experience a brief period of stability before decay begins, because there is no such thing as a moment free from perturbation in a universe where electromagnetic radiation fills all of space and quantum fields fluctuate everywhere, and so the white hole exists, if it exists, in a state of immediate crisis, its formation and its dissolution not sequential events, but overlapping processes, simultaneous rather than consecutive. This is not destruction in the usual sense, where an object first exists in a stable state and then encounters some force or condition that breaks it, but rather a failure to cohere in the first place, a structure that cannot finish assembling before the forces preventing its assembly overwhelm it, like trying to build a sandcastle while waves are already washing over the construction site. Each handful of sand placed immediately undermined by the water that was there before the building began. The white hole flickers, if flicker is even the right word for something that never fully transitions from potential to actual, that never completes the process of becoming before the process of ceasing begins. That exists only in the mathematical sense of being a solution to equations, without ever being an object in the physical sense of persisting through time and occupying space in a way that other objects can interact with and observe. And so the first second is also the last, except there is no first second, no interval that could be marked on a clock or measured by an instrument, only the briefest perturbation in space-time geometry that appears in the mathematics as a white hole, but in reality as something far less defined, far more transient, far more like a failed possibility than a realized object. And by the time anything could detect it, the conditions that allowed it have already vanished, and what remains is ordinary space-time, slightly disturbed perhaps, but unmarked by any lasting signature of what almost was. The universe doesn't fight white holes because fighting implies opposition, implies effort, implies that the white holes are substantial enough to resist. But white holes are not substantial in this way, are not robust enough to merit opposition, and so the universe simply continues as it always does, its fields propagating, its particles moving, its space-time evolving according to the stress energy within it, and the white hole that might have been disappears not into the universe but into the category of things that could not maintain themselves even momentarily, that existed only as equations suggest they could, but reality confirms they cannot. The first second is the last, because there are no seconds at all, only the immediate negation of possibility, only the instant collapse of potential into absence. The fundamental equations of physics, Maxwell's equations for electromagnetism, the Schrödinger equation for quantum mechanics, Einstein's field equations for gravity, all possess a particular property that physicists call time reversal symmetry, which means that if you take any solution to these equations describing some physical process and reverse the direction of time, replacing every instance of t with minus t, you get another valid solution, another process that obeys the same laws even though it runs backward through time, and this mathematical property suggests a kind of fundamental even-handedness in nature, an indifference at the deepest level to which direction time flows, forward into what we call the future, or backward into what we call the past. White holes emerge directly from this symmetry as the time-reversed version of black holes, and because black holes are solutions to Einstein's equations that describe regions of space-time where matter collapses inward and nothing can escape, white holes become solutions that describe regions where matter emerges outward and nothing can enter, and both solutions are equally valid mathematically. Both satisfy the field equations with the same rigor. Both represent allowable configurations of curved space-time that respect all the fundamental laws governing how mass and energy shape the geometry of the universe. But the universe we inhabit does not exhibit this symmetry in its behavior, even though the laws permit it, because if the laws were the only thing that mattered, then we should see white holes and black holes in equal abundance, should fine matter emerging from regions of space-time just as often as matter collapses into them, should observe processes running backward through time just as commonly as processes running forward, and yet we see none of this. See instead a universe where time has a clear direction, where certain processes happen readily and their reversals never occur, where eggs break but never spontaneously reassemble, where heat flows from hot objects to cold ones but never the reverse, where causes precede effects and not the other way around. This asymmetry emerges not from the fundamental laws but from something more subtle, something called the thermodynamic arrow of time, which points in the direction of increasing entropy, increasing disorder, increasing randomness in the distribution of energy and matter, and entropy increases not because any law requires it, but because there are vastly more disordered states than ordered states, vastly more ways for energy to spread out than to concentrate, vastly more configurations that look random than configurations that look organized, and so systems naturally evolve toward the more probable states, toward higher entropy, toward greater disorder, not because they must, but because the odds overwhelmingly favor it. Black holes fit naturally into this thermodynamic arrow because they represent the ultimate increase in entropy, taking matter that was spread out across space, in stars, in gas clouds, in planets, and concentrating it into a region so dense and so gravitationally extreme that all structure disappears, all information about the original configuration becomes inaccessible, and the black hole itself, according to Bekenstein and Hawking's insights, possesses enormous entropy proportional to the area of its event horizon, meaning that the formation of black holes increases the total entropy of the universe, moves the cosmos in the direction it already tends to move, aligns with the thermodynamic arrow rather than opposing it. White holes would require the opposite, would need entropy to decrease, would need matter to emerge from a region of maximum disorder, the white hole's singularity where all structure has collapsed, and spontaneously organize itself into particles with specific energies and momentae, streaming outward in coordinated patterns, and while this does not violate any fundamental law, does not break conservation of energy or momentum or charge, it runs counter to the thermodynamic tendency so strongly that the probability of it occurring becomes vanishingly small, not impossible in the strict sense, but improbable that waiting for it would require timescales vastly longer than the age of the universe, longer than the time until the last stars burn out, longer than the time until protons themselves decay if they decay at all. The metaphor that captures this is a room full of air molecules, all bouncing around randomly, colliding with each other and with the walls, and if you wait long enough, unimaginably long, there will come a moment when by pure chance all the molecules happen to be moving in the same direction, all their random motions briefly aligned, and at that moment the air in the room would spontaneously compress into one corner, creating a vacuum in the rest of the room. And this configuration is not forbidden by the laws of physics, is in fact a valid solution to the equations of thermodynamics, but it is so spectacularly unlikely that it will never happen during the lifetime of any observer or any civilization or any galaxy, and white holes are similar, are valid solutions that never occur because their occurrence depends on a kind of cosmic coordination that probability renders effectively impossible. The laws permit it, the tendencies prevent it, and the tendencies are strong not because they impose strict prohibitions, but because they shape the landscape of possibility in ways that funnel outcomes towards certain paths and away from others, making some configurations common and others rare, and others so rare they might as well be forbidden, even though technically they are not. And white holes fall into this last category, permitted by the symmetry of the fundamental laws but blocked by the asymmetry of the thermodynamic arrow, which is itself not a law but an emergent property, a statistical tendency arising from the sheer number of possible states available to any system. This means that time reversal symmetry, while real and while important for understanding the deep structure of physical law, does not translate into symmetry in the actual universe we observe, because the universe began in a very special state, a state of extremely low entropy where matter and energy were distributed almost uniformly with only tiny fluctuations. And from that special initial condition, the universe has been evolving toward higher entropy ever since, expanding and cooling and allowing structures like stars and galaxies and planets to form temporarily as local decreases in entropy paid for by larger increases elsewhere. And this one-directional evolution, this thermodynamic arrow, is what gives time its felt direction, its asymmetry, its sense of flowing from past to future, rather than simply existing as a dimension we can move through in either direction. White holes would need to appear in a universe running backward, a universe where entropy decreases, where effects precede causes, where the thermodynamic arrow points the opposite direction. They do not fit here. They fit somewhere else, in some other cosmos where the initial conditions were different, where the thermodynamic arrow points another way, where the tendencies that govern outcomes align with decreasing rather than increasing entropy. But that is not our universe. Our universe chose a direction at its beginning, chose low entropy, chose the conditions that allow black holes to form naturally and white holes to remain absent. The choice was not written into the laws, it was written into the initial state, and the initial state, once set, determines everything that follows. Symmetry is not permission. You can feel weight because the ground pushes back, your body pulls downward. Gravity acts on every atom, the floor resists. The compression creates sensation. Without the ground, you'd fall. Without resistance, there's no weight. Connection creates experience. Physics works the same way. A particle exists not in isolation but in relationship. An electron has charge, so it couples to the electromagnetic field. It has mass, so it curves space-time. It has spin, so it responds to magnetic fields. These aren't separate properties, they're connections. The electron pulls on the field pulls back. The exchange is what makes the electron real, makes it detectable, makes it persist. Remove the connections and you remove the particle, not instantly, not dramatically, but you remove the mechanism that allows it to continue. A particle cut off from all fields, from all interactions, would not explode or vanish in a flash. It would simply stop being anchored to the structure of reality. It would drift out of existence the way a thought drifts when you stop attending to it. White holes would face this problem from the start. They would need to exist without accepting input. No particles could fall in. No fields could penetrate the horizon. No gravitational waves could disturb the interior. The white hole would be perfectly isolated, cut off from everything outside, unable to participate in the exchanges that bind objects to the universe. This isolation would make persistence impossible. Think about how ordinary objects maintain themselves. A star burns because it's connected to the quantum fields that govern nuclear fusion. Protons in the core collide. Energy releases. Photons carry that energy outward through layers of plasma, through the photosphere, into space. The process continues because the star is embedded in an environment that supplies fuel and removes heat. It's an open system, Energy flows in and out. A planet maintains its orbit because it's connected gravitationally to its star. The star's mass curves space-time. The planet follows that curvature. The relationship is continuous. Information about the star's position propagates through space-time at light speed, constantly updating the curvature the planet responds to. The orbit persists because the connection persists. Even black holes maintain themselves through connection. Matter falls in, the black hole grows, its event horizon expands. The process is one way, but it's still an exchange. The black hole receives, it accumulates, it changes in response to what enters. And through Hawking radiation, though the effect is tiny, black holes also emit, slowly returning energy to the universe over timescales longer than the current age of the cosmos. The connection is asymmetric, but it exists. White holes would allow no such exchange. They would emit constantly, releasing particles and radiation without ever receiving anything in return. An emission without replenishment is not sustainable. You cannot give indefinitely without taking. The white hole would need to draw energy from somewhere to fuel the emission. The only source available would be its own gravitational field, its own space-time curvature. As particles leave, they carry energy with them. The curvature weakens, the white hole shrinks, but this shrinking is not the main problem. The main problem is that the white hole cannot adjust to its environment. It cannot respond to the pressure of accumulated matter outside its horizon, cannot adapt to the distortions caused by nearby objects, cannot correct for the perturbations introduced by passing gravitational waves. It must remain perfectly rigid in its geometry, perfectly unchanged by the universe around it. And perfect rigidity is not something space-time allows. Space-time flexes, it ripples, it responds dynamically to everything in it. When two black holes merge, space-time shudders. Gravitational waves propagate outward, carrying information about the collision. The waves stretch and compress space itself, passing through galaxies, through planets, through detectors on Earth that measure the oscillations. This is space-time adjusting, responding, carrying energy away from the source. A white hole could not participate in this kind of adjustment. It could not flex, could not ripple, could not absorb the passing gravitational waves or allow them to alter its structure. The waves would deflect around it, bending away from the event horizon, never touching the interior. The white hole would remain unchanged while the universe around it evolved, and this unchanging nature would make it fragile. Because rigidity in a dynamic environment leads to fracture. A tree that cannot bend breaks in the wind. A structure that cannot flex cracks under stress. The white hole, unable to adjust, would accumulate stress at its boundaries. Small distortions in the geometry where the rigid structure met the flexible universe, where the isolated object pressed against the connected cosmos. These stress points would grow. Each deflected particle would add to them. Each passing wave would increase them. The stress would concentrate at the event horizon, the boundary between the white hole's refusal and the universe's insistence. And eventually the boundary would fail, not because something broke it from outside, but because the stress built up to the point where the geometry could no longer maintain its shape. The failure would be quiet. No explosion, no release of energy, just a gradual warping of the horizon, a slow dissolution of the boundary that separated the white hole from everything else. The event horizon would become permeable. Particles would begin to cross inward. The white hole would start to receive, to accept input, to participate in exchange, and the moment it began participating, it would stop being a white hole. Because a white hole is defined by refusal, by isolation, by the absence of anchor. Remove the refusal, and you remove the definition, the object that remains might still curve space-time, might still have mass, but it would no longer be white. It would be something ordinary, something connected, something that could persist because it had anchored itself to the rest of reality through the simple act of allowing the exchange. Duration requires connection. White holes would refuse connection, and so they would have no duration. Not because they were destroyed, but because they were never anchored in the first place. They would exist as mathematical possibilities, as solutions to equations, as structures that could be described but not realized. And the reason would be simple. The universe does not support isolated existence. Everything touches everything else, however faintly, and white holes would need to remain untouched to remain white. The anchor is what allows things to stay. White holes would have no anchor, and without it they'd drift away from being, not into non-existence, but into irrelevance, into the category of things that almost were but couldn't quite manage to continue. There are questions in physics that close cleanly. The orbit of Mercury, once puzzling, was explained by general relativity. The photoelectric effect, once mysterious, was resolved by quantum mechanics. Dark matter remains unidentified, but most physicists believe it will eventually be detected, categorized, understood. These are questions waiting for answers. White holes belong to a different category. They are questions that might not have answers, not because we lack the tools or the data, but because the question itself exists in a space between mathematics and reality where answers become ambiguous. The equations say white holes are possible. Observation says they are absent. And the gap between these two statements is not something more data will necessarily close. This gap appears elsewhere in physics. Magnetic monopolies, particles carrying a single magnetic pole, north or south, but not both, are allowed by Maxwell's equations. They fit naturally into certain quantum field theories. They should exist. Yet we have never found one. The universe could contain them. It simply chooses not to, or chooses to hide them so effectively that billions of years of cosmic history have produced none we can detect. Tachyons, particles that travel faster than light, appear as solutions to relativistic equations. They are not forbidden mathematically, but they lead to causality violations, to paradoxes, to situations where effects precede causes. And so they do not appear, not because a law prevents them, but because the structure of space-time does not accommodate them. White holes fit this pattern. They are mathematically sound but physically absent. The universe contains the conditions for black holes, massive stars, collapsing cores, regions where matter concentrates, but it does not contain the conditions for white holes, or rather, it contained them once, possibly, in the first moments after the Big Bang, when space-time was still forming and the rules were less settled. Some cosmologists have speculated that the Big Bang itself might be understood as a kind of white hole, a singularity from which all matter and energy emerged, expanding outward into the space that would become our universe. The comparison is imperfect. The Big Bang was not an object in space, but the origin of space itself. It had no event horizon, no boundary separating an interior from an exterior. But the structure is similar, a point from which everything emerged. No prior state, no cause, just sudden total expansion. If this comparison holds, then white holes existed once, 14 billion years ago, in a form so extreme and so brief that it defies normal categorization. And if they existed then, they have not existed since. The universe cooled, space-time smoothed, the conditions that allowed emergence without history disappeared. What remains are black holes, which accumulate, which persist, which fit the thermodynamic arrow the universe now follows. But the question lingers. Could white holes form again? In the far future, when the universe has expanded beyond recognition, when the last stars have burned out and the cosmic microwave background has cooled to near absolute zero, will the conditions change? Will entropy continue increasing until some maximum is reached and then reverse? Will time's arrow flip, allowing processes that now seem impossible to become commonplace? No one knows. The physics of the far future is speculative. We can model how stars will die, how black holes will evaporate through Hawking radiation over timescales of 100 years, how protons might decay if they are unstable on long enough timescales. But we cannot predict with certainty what the universe becomes after all structure is dissolved, after all energy is spread so thin that nothing happens anymore. Some theories suggest a heat death, a state of maximum entropy where no gradients exist, no differences in temperature or density, nothing to drive change or allow events. In such a universe, white holes would remain absent because the conditions for their formation would remain absent. Other theories suggest cycles, universes that expand and contract, big bangs followed by big crunches, followed by new big bangs. In such a cosmology, white holes might reappear with each cycle, brief anomalies in the moment of transition. But these are speculations, not predictions. The question remains open, and perhaps that is the right place for it to remain. Not every question in physics demands closure. Some questions serve a different purpose. They map the boundary between what is known and what is unknown, between what the equations allow and what reality implements, between the symmetric beauty of fundamental laws and the asymmetric messiness of actual outcomes. White holes mark this boundary clearly. They show us that the universe is not obligated to explore every possibility the mathematics permits. They show us that symmetry in the laws does not guarantee symmetry in the cosmos. They show us that existence is more than satisfying equations, more than being logically consistent, more than fitting within the theoretical framework. Existence requires context, requires compatibility with the environment, requires the kind of stability that comes from connection rather than isolation. And they show us that absence can be as informative as presence. The fact that we do not observe white holes tells us something about the universe's initial conditions, about the direction of time, about the role of entropy in shaping cosmic evolution. It tells us that the universe began in a low entropy state and has been evolving toward higher entropy ever since. It tells us that the thermodynamic arrow is not a mere statistical tendency, but a fundamental feature of our cosmos, strong enough to suppress entire classes of solutions to the equations of physics. So the question remains, not because we lack the answer, but because the answer exists in the space between certainty and speculation, between the mathematical and the physical, between what could be and what is. White holes hover in that space, almost real, almost possible, flickering in the equations but never quite solidifying into existence. And perhaps they will remain there, in the mathematics, in the thought experiments, in the boundary cases where physicists explore the limits of their theories. Perhaps they will never be more than solutions on paper, descriptions of objects that cannot survive their own physics, examples of how the universe selects among the possibilities the laws permit. Or perhaps somewhere in the cosmos, in conditions we cannot yet imagine, a white hole exists for the briefest moment, emitting its contents into space, dissolving before anyone could observe it, leaving behind only the faintest trace that something strange occurred. And that trace, too faint to detect, too brief to measure, fades into the background, indistinguishable from the random fluctuations that fill the universe at every scale. What remains is the question, and the question, unanswered, is enough. Thank you for listening. If you'd like to support this channel, consider leaving a like or subscribing. It helps more people find these quiet explorations of physics. Until next time, rest well.